So today, Carrie and I will talk about the section 3.4, concavity and the second derivative test.
And the content today is going to be in 4 parts: introduction, example, classwork, and homework.
So here is a definition of the concavity. That f be differentiable on an open interval. The graph of f is concave up if the derivative of f is increasing on the interval, and concave down if derivative of f is decreasing on the interval. Here is the picture of concave up and concave down. So there are two conditions to do the test for concavity. And if the second derivative of f is bigger than 0 for all x in the interval, the graph is concave upward. And if the second derivative is smaller than 0, then the graph is concave down. So here's the first example. F of x equal to x to the power of 4 minus 4x to the power of 3 plus 2. First, we find the first derivative of the function, and after that, we find the second derivative. And through the second derivative, we can get the two solutions of x. And based on the solutions, we can get this table, which have x value and the sign of the second derivative of f of x. And through the table, we can get from negative infinity to 0 and from 2 to positive infinity. These two areas are the concave up, and from 0 to 2 is the function is concave down. And here's a definition of points of inflection, which means if the graph of f changes concavity at that point, then this point is a point of inflection of the graph of f. And if the point c, f of c, is a point of inflection of the graph of f, then either second derivative equal to 0 or second derivative does not exist at x equal to c. So here is another example. Through the original function, we can get the first derivative and the second derivative. And then we can get the solution of x. And through the solution, we can get this table. And from this table, we can see when from negative 1 to 0 and 0 to positive infinity, the function is concave up, and from negative infinity to negative 1, the function is concave down. And the point of inflection is when x equal to negative 1. So here's the second derivative test. If the second derivative bigger than 0, then f has a relative maximum, and if the second derivative less than 0, it has a relative maximum. And if the second derivative f of c equal to 0, then the test is inconclusive. So here's another example. From the original function, we can get the first derivative and second derivative. And we put x equal to 1 into the function, and we can get this formula to calculate y if we put 1.1 into the function, to the equation, and then we can get y equal to 5.6, which means f of 1.1 is approximately equal to 5.6. So here's a 4 graph which shows the different function with how to determine the concave up and concave down, or the underestimate and overestimate.
And this is the homework of this section. First question, it asks us to state the signs of first derivative and second derivative form of a function on the interval from 0 to 2. In this question, we can find that since the curve is actually is facing the downside, so the second derivative will be smaller than 0, and since the line is toward upward, so the first derivative will be greater than 0. And for this question, it's going upward, and also it's going down because in this direction. So it would be negative in first derivative, but concave up, which means the second derivative will be positive. In this question, it asks us to find the points of inflection and discuss the concavity of a graph of a function. So we need to find first the first and second derivative form of a function. Then we can find the points when second derivative form is equal to 0. We found x equals 2, then we can make the interval before and after 2. Then calculate the positivity. We can find that concave concave up happens from 2 to infinity and concave down from negative infinity to 2. In this question, same method to find the second derivative, find the point of inflection, make it equal to 0. Then find the interval and their positivity, and we can find where a concave up is from negative infinity to 0 to negative 2, and from 0 to positive infinity. And where concave down is from negative 2 to 0. Question 24. This question will be a little different because here there's a square root under. So we have to consider the x equals to 0 because it won't happen. It won't occur here. We use the same method to find the x, which equals to 9. Then we can find the interval. We have to make 0 on it. And concave up, the interval will be from 0 to 9, and concave down will be from 9 to infinity. Question 33. It asks us to find the relative extrema, which will be a little confusing, and I'll talk about it with the question. We're going to find the points on first derivative form, which is to find the extreme points. Then we're going to find, we need to plug in the extreme points on the second derivative form. And here when it's negative, which means that the concavity will be concave down, and here when it's positive would be up. So here the points would be maximum, and here the point would be minimum. So when it's positive on second derivative will be minimum point, and the extreme, while it has negative in second derivative, will have the point of maximum extreme. So this question would be maximum is at x equals to 0 and minimum at x equals to 2. And in this question, same method, we need to find the extreme point, then plug in the number into second derivative form to find the number. So here is positive and negative. So we'll have maximum at x equals to 3 and relative minimum at x equals to 5 over 3. In question 50, first question, so since the rate of change of cells is increasing, so second and first derivative will be all positive. And in B, cells are increasing at a slower rate. It's increasing at first, which means the rate is positive, but it's at a slower rate. So it means first derivative is positive, but second derivative will be smaller than 0. In C, the rate of change of cells is constant. This tells us the rate of change, which is second derivative, will be equal to 0, but it doesn't tell us if it's actually increasing or decreasing. So first derivative will be unknown. And so in D, cells are steady, which means everything the same. And in E, cells are declining, which means here in first derivative form it will be smaller than 0, but it's at a slower rate. Because it's at slower rate and declining. Declining means it's smaller than 0, but slower rate means they have different signs. When it's have the same signs and the first derivative is smaller than 0, then it will declining in a faster rate. So in F, cells have bottomed out and have started to rise. It will have two trends. First derivative will from negative to constant, and the second derivative will always rising. In question 77, if first derivative form of f larger than 0, then f is concave upward at x equals to c, which won't be correct because this one cannot tell us the concavity. Concavity can only be shown by second derivative form. So it's false. An increasing function can be concave up or concave down. And in the last question, the graph of f must have a point of inflection at x equals to 2 if second derivative of form of f of 2 is equal to 0, which is false because we need to know the interval, because when x is smaller than 2, x larger than 2, here might be 0, but here that might have the same sign. If it's the same sign, it won't be a point of inflection. So it's false. Points of inflection only occur where the graph changes concavity. And that's it. Our presentation is over.
I think that's all. Thank you.